That's right.
Mm-hmm.
The first week I wasn't involved in the school.
Yeah. Yep.
So
I think your AA should know that. They're the one who doesn't know your division. You just inform them that you change
but
class or what?
yeah,
I think you do know who's your AA? There's the officer that in charge of your program.
okay.
Yeah, you should. I mean,
his
maybe
email.
you email this
Yeah,
email address
yes,
and then
yeah.
you just. Oh yeah, sure. Yeah. Reply to her that you change class and Okay, good morning to everyone. So let me find one person. It's Tu Jiawei here. And we'll record that Tu Jiawei is not here at 9 o'clock. So later I will ask him. See when he appear. Tu Jiawei is not here. Tu Jiawei. Okay, let's check when he appear. Okay, so let's find this null space of this matrix here. So what you're gonna do to find the null space of this matrix? Sorry, one by one. Who want to say? Who want to say or no? Ah, sorry. So how to find it? In the It's the form. Yeah, what's the form? Parametric vector form. So you want to find the solution. Solution to what? Solution to what equation? You need to have equation to solve, right? So what's the equation? The homogeneous linear system. Okay, or the augmented matrix with B vector 0, 0, 0. Okay. So from here, what's your solution? How do you read out the solution here? So okay, first of all, how many pivots? P, right? 1, 2, 3 here. Meaning there are two more free variables. Okay, you can calculate from the rank theorem also, right? Dimension of code A equals to the dimension of, dimension of code A plus dimension of now A equals to the total number of vector. Okay, so in this case here, the rank theorem says 3 plus 2 equals to 5. Okay, because the total number of vector is 5. So first is rank A. So let's say we call this A, and then 2 is dimension of now. Okay, so now we want to identify which two vector serve as a basis for your now A here. Okay, which vector? So let's read out the parametric. So this is equal to what? S3 times 3 minus 4. Sorry, minus 3. Okay, so I don't want this. Maybe I swap this number a bit. So let's use this. Okay, let me think. S3. Yeah, I think this is what I want. Okay, minus 3 and then minus 4, right? Okay, and then 1, right? And then 0, and then 0. And plus what? S4 times x3 minus 3, and then minus 4, 0, 1, 0. Okay, so the question is, if we take this, so what we see is the span of this solution, right, is a linear combination of these two vectors here. Okay, but do you know that why they are linearly independent or not immediately? What? Oh, okay. You mean you take this two vector and then check the row reduced form. Is it? You mean if you form a matrix using these two vector and then you found that there are pivot in every row, every column.
So close to 0, 0, 0.
You mean set the whole thing equals 0? Yeah, that's right. So then to solve that, you have to do the REF. So this means you just row reduce the matrix form. Okay, but Senai asks why is it always true actually? Actually, it's always true. Why can you just pick these two as your basis? So why these two automatically scan? Right? Okay, yes, this is one thing I mentioned in class, position of one. Okay, because you see, this is the worst case already. Worst case, other than this two position here, they are the same entry. This is the worst case. But you also learned in the class, right? What did you learn in the class? Rank theorem. Okay, we know that the rank A is 3 because pivot column will form basis. This is the theorem. Okay, so we know that this 3 happens. This 5 you already know also because you just count 5 of them. So what I meant is you know that the dimension of now A already is 2. So there's a theorem tells you, right, if you know the subspace dimension, what else you need to find the basis? Two ways, right? Either you find two linearly independent vector, or you find two vector that span. Here is the two vector that, so you can immediately take these two as your basis. Yes. Okay, or technically, like what she said, you can see that the position of one is different. Not just position of one, also with help of these zeros. This is already the worst case, I think. That's the worst case. Other than this S3 and S4 position, they are the same entry. Yeah, but I think it's this part here. I think if you want to show without the theorem, this 1001 is the one that you have to find the people. Okay, yeah. But anyway, in class, I mean, in exam, right, you can straight away take these two as your basis. Okay. And the reason is one, you can use rank theorem. The other one is you identify out this 1001. Any other question? Before I do some recap. Any question? Okay, so if no question, I want to do some recap before we go to new stuff today. Let's tell another story. So I want to tell this story from 4.2. Actually, this one we skip. So I mean, why we skip? I think you can read yourself because it's very similar to what we taught last time. And if needed, we will come back in chapter 2 again. Okay, but I want to introduce some definition there. So for example, because you guys say that you are weak in linear transformation, so let's start with linear transformation definition. But we're going to introduce linear transformation in a more general setting. Let's start with two vector spaces. Okay. Last time we start with Rn and Rm, and not equal to n. But now we go general. Okay. V and W here. So what's the linear transformation? So a linear transformation between, okay, not use between, let's say from V to W so that we know who is the domain and codomain. It's simply a function, okay, function from V to W. Okay, let's call our linear transformation T here. Okay, to W. So what's the function? Function is very easy. Function is the thing that I feed you an input, you give me an output. That's all. Yeah, I feed you an input. You only feed me one, you cannot feed me more than one. Otherwise, I will confuse. Then otherwise, the function will confuse. So one input, one output. But this one has special condition. Okay, two special condition. Okay, so you need to remember. One is preserving vector addition. Second is preserving scalar multiplication. Okay, such that for every vector v1, v2 in V, okay, so I can add them up first, right? Because vector space is closed under addition, so it's still an element in V, so I can fit this element to T. But what does T give me? T actually split the sum up. Okay, T split the sum up. Okay. Second, if I take any scalar, okay, let's fix our scalar, multiply with my V, I still live in V because vector space is closed under scalar multiplication. Okay, so I can fit it to T also. Okay, T should give me something. What does T give me? It just split the C up also. Okay, so as long as your map satisfies these two properties here, okay, and it is from a vector space to the other vector space, then it is a linear transformation. Okay, so think again, geometrically, how to think about it. V1 plus V2 is what? It's a point that, okay, so let me write here. So V1 plus V2 live in what? Live in the span of V1, V2. Okay, meaning what? If you take a V1 and then you take a V2, okay, you look at all the span. Look at all the span means what? You look at all the plane. What happened? It sends to another plane. Why? Because this plus here means what? TV1 and TV2 live in where? Live in the span of TV1, comma, TV2. Okay, meaning what? It sends a point in a plane to another plane in your coordinate. How about this one? Can you guess what happened to this? TV1 is a point in where? Span of V1. Span of V1 means what? Is a line. C times V1 is a span of T V1. So meaning what? Linear transformation will send line to line also. Okay. So linear transformation send points, send planes to planes, also send point to, send line to line. Okay, no. Okay, so this is the geometric meaning of these two properties. Okay. Yeah, so maybe I give you one more example before we go to the next part of the story. So example is, let's do a non-trivial one. D over dx is a linear transformation from, let's say, let's do it less general, maybe P3 to P2. Okay, I was informed by last short sem Chinese student that they never seen this before. Does all the Chinese students seen this before? Differentiation. You guys know this? Most of you know this? Or any one of you not know it? Because there's one student, the exam question, I have this notation. The student told me he never see this before. So what can I do? I mean, I did mention in class, but I didn't define it properly. So in this time, I think I should define it properly. So, okay, so I said that this is a map, right? So I need to tell you in general what happens to the element for P3. But in general, the elements in P3, how you see it? How do you write it down? What is P3? Okay, what is P3? Set of polynomial with degree at most 3. So how do you write down the general polynomial? A plus bx plus cx squared plus dx cubed. Okay, so you stop here. Okay, so this map, what does this map do to this? I fit this polynomial into this d over dx. What should split out? E plus 2cx plus 3dx. Okay, so you can see that indeed the thing that you split out is at most 2 degree. Okay, land in the right place. So my claim is this is a linear transformation. Okay. So to educate all right, I can generalize this too. So before doing that, we can generalize this d over dx to Pn from Pn to Pn minus 1. Okay, so what does this d over ds do is you, okay, let me write down first. A0 plus A1. Okay. So what you do is you look at each, we call it monomial here, each monomial here, okay, decrease the power of x by 1. Okay, decrease the power of x by 1, and then multiply the monomial with the previous power. Okay, so this is what we do here. So this elements here will get sense to. Okay, let me right here. So here is A1 plus A2x plus up to, sorry, here is 2 times A2x and then 10 times AN2. Okay, so you might want to ask, where does the constant go? Where does the constant go? We just send it to 0. Okay, so this D will send the constant to 0. Okay, how shall we? Good morning. Morning. Okay, so we send this constant to 0. All right, so we want to prove that this is a linear transformation, right? So there are 2 things to check here. Okay, so there are 2 things to check here. So d over dx on 2 polynomial. So let's set 2 polynomial first. Let px equals to a1 plus b1x plus c2x squared. Sorry, c1x squared d1x squared cubed. Sorry, qx equals to a2 plus b2x plus c2x squared plus d2x squared x cubed. Okay, so now you want to do d over dx on px plus qx. Okay, and then we want to show that this is equals to, so what's our goal here? So let's put our goal. Okay, our goal is to show that this one is equals to d over dx on px plus d over dx on qx. Okay. Okay, I want to teach you another method to do max. You could do max backward. What do I mean by backward? So if you compare these 2, right, I think this is easier to understand. I don't know, because we differentiate. We define this, we call it differentiation operator here. Differentiation operator on a single polynomial. Okay, this is what we define right just now. Okay, so maybe we can work backward. Okay, let's try and work backward. Since we want them to equal, right? So you can go down and go back anywhere you like. So let's go backward. Okay, so this is how I teach my math students, because we need to prove, right? Proof is quite abstract, so they get they easily get lost inside the proof. So how to not get lost? You need to always remember your goal. Okay, this is similar in your life also. Okay, you must remember your life goal. Otherwise, you will lost in your life. Okay, so let's work backward from this goal here. So by definition, right, how to differentiate PX? Maybe let's get one of the Chinese students to answer. Okay, who want to answer? Let me call name. Let's call someone. Lin Xingyu, see or not? Ayo, cannot. You cannot. Too good. I call someone else. You are good, so I don't want to consider. Tao Ziyu. Okay, no, wait. You are good also. Wait. Let me change someone else. Hu Shenyu. Hu Shenyu, I think is front here. Okay, let's try Hu Shenyu. What is d over dx of px? S2. Okay. Enough. Okay. How about so just now who I call? What's your name? Just now I call you. The white hair girl. What's your name? How's the is this correct or not? Why? So okay, it should be 2c1 plus 3d1 x squared. So you need to remember you bring the all power down. Okay? You need to remember. Okay, please remember differentiating. So let me write down differentiating a monomial here. So let's differentiate a to the x to the power n. Please remember that you bring the n down and then you take the n minus 1. Okay? Alright, please remember this. Okay, let's do the other one. Let's try different people. 林思成 here or not? 哎，不可以，我再换一个人啊，我再换一个人。Okay, let me just check from the quiz. How about Ngu Yan? Ngu Yan is Ngu Yan here? Ngu Yan not here. Is she not taking quiz today? How about Nicole Tong? Xin Yi, right? How to differentiate QX? C2 x plus 3 D2 x2. Good, very good. Okay, so we do to this stage. So what can you see here? One thing you can do is you group the term with the same degree, right? So we put b1 plus b2 plus 2c1 plus 2c2 times x plus 3d1 plus 3d2 times x squared like that. Okay, so the problem is this equal to the derivative? Okay, we call it derivative of px. That's true. Okay, why? So maybe one more step will make this thing clear. Maybe two more steps because we need to write down the qx and px. So what's px here? So a1 plus b1x plus x. X plus c2 x squared plus c2 x cubed. Okay, then what do? You also do the grouping by polynomial with the same degree. Okay, only when you write into this polynomial form, you can apply the what? The definition here. Okay. So all your scalar here become a sum of scalar. Okay, yeah. So you can see that the degree 0 term disappear. Okay. The A term here disappear. Okay or not? Any questions so far? Any question? Question? No? Okay, so if no, I left the second one for exercise. You can go back and try the same method. Okay, so this is another example for linear transformation. This is kind of useful. Maybe in chapter 5 we'll meet it. I think in exam you also will meet it. All right, so let's tell the story that we had last time. So first of all, we start with a vector space, okay, V. So we know that this V is a linear combination of bunch of vector, maybe infinite of them. Let's draw this picture. Let's draw the picture. Vy. Okay. So okay, let's say we know that this dimension of V is some finite n. So what happened here? Okay, what happened here? Using the spanning set theorem, so here is a spanning set theorem. What can we do? We can throw away all the linear dependent vector such that it is still equal to the span of some B1 up to Bn. Okay, so meaning we just need to use n vector, okay, to build the whole space. Right. Okay. So what does it mean here? So by oh, this is one. Next. So by the how do we call it? The unique representation theorem. Every V, okay, inside your vector space, you can express as a linear combination of your basis vector. Okay. And also, what's the unique part here? Do you remember what's the unique part here? What's the unique part here? The unique part here is the uniqueness of all the scalar. Okay, meaning what? One vector, one element in your vector space, there's only one scalar that can fit to this linear combination. Okay, so from here, what's the construction? From here, we build a construction to Rn. Okay, to Rn. How to build this construction? We send this V to the set of, the vector that consists of the coefficient. Okay, so this is what we do. Okay. So the fact that this existence and uniqueness says that this map is 1-to-1 and I say onto, yeah, onto. Okay, 1-to-1 and onto. We didn't prove this in class. Okay, we didn't prove this in class, but I give you the notes. Okay. If you don't read the notes, maybe you just take my word. Then if you don't want to take my words, try and understand my note. Okay. Yeah. So onto is very easy, right? Okay. Any vector in Rn, I just fit into this linear combination, then I will get a vector here. Okay, so this is how you check onto. Why is it 1-to-1? Because this scalar is unique. Then one set of scalar only pair with one vector. There's no two different vector get sent to the same scalar. Okay, so it's 1, 2. Okay, so why is this good? So I talked quite fast last time, right? So I said that there's a bijection or an isomorphism here. Okay, so here I will say that vector space. Okay, so here is a bijection. Okay, so bijection just means 1-to-1 plus onto. 1-to-1 plus onto become bijection. Okay, and then one can check that. One can check that this is also a linear transformation. Still remember how we write this map down? What's the notation for this map? Or what's the name of this map? Anyone remember? What's the name? What's the construction that I give you a V, you give me a set of CI? What's that name? How is C? Coordinate vector. Good, very good. So it's bracket, dot, and then a basis here, right? Okay, so what's this B here? So basically this B is this B1, 2. Okay, coordinate vector, very good. So this one is called coordinate. Okay, so this is the coordinate vector. And we can prove that this is a linear transformation. It is 1-to-1 and onto. So it becomes so all these three together will become the isomorphism. Okay, so a moral about this isomorphism is whatever you want to do computation on the right hand side, you can do the computation on the left hand side. Okay, so you can go back and forth. Okay, let me show you an example. Last time I didn't stress on this, right? Because I don't want to. I think today you are a bit more prepared. So let's do some example. Okay, let's do V when equals to P, let's say P2. And what do you reckon? What can you write this as? So just now we know that a general elements here looks like A plus BT plus CT squared. So what do you reckon? What can you write it as? Span of what? If judging from this element here. So you can see that A, B, C is living in R, right? Okay, so they are like a scalar. So what can you pick as a basis? Okay, this is a very natural choice to pick, right? Okay, but now I'm going to show that these are bases actually. Right, these are bases. Actually, span is easily to see, right? Span is easy to see. Okay, but why is it linearly independent? Okay, why is it linearly independent? And if we apply this construction, if we apply this construction of coordinate basis, what happens? What is the codomain you should land in? Which Rn? How many coefficient here? 3. Okay, so supposingly you should land in R. Okay, let's try this. Okay, let's try this. Right. So we want to show that. So here is our. Okay, I put WTS want to show. Okay. So I want to show that 1t squared is a basis for. So first, span is easily to check. Okay, span is easy to check. So what's span here? So say that expand P2 because for every P in P2, let's say PT lah. PT in P2, we can write it as PT equals to A plus BT plus CT. for some A, B, C. Okay, so this one is easy because we know that every element look like this. But how about linearly independent? You see that 1t squared is linearly independent. We need to check what? Definition. I really repeat for how many lectures already. So what's the definition? We need to check that if C1 times 1 plus C2 times T plus C3 times T squared T squared equals 0 implies that C1 equals to C2 equals to C3 equals to 0. 0 is the only solution. But last time, what did I tell you? How to equate two polynomials together. How to equate two polynomials together? There must be the same in each coefficient. Okay, there must be the same in each coefficient. But here only got 0. So on the right hand side, what's the coefficient for degree 1 polynomial? What's the coefficient for degree 1, degree 2 polynomial? Huh? 0. Yes, 0. So actually, your 0 polynomial should look like this. 0 plus 0 times t plus 0 times t squared and so on. Okay, this is the true form of your 0 polynomial. Okay, not that this is equal as 2 polynomial. Or this implies that C1 has to be equal to 0, C2 has to be equal to 0, and C3 has to be equal to 0. Okay. Okay, so this is how you check. Okay, if you're gonna check P2 is, to find basis in P2. But we can also do similar computation on R3 here. Okay, so this is the accent of this coordinate vector here. So in this case here, 1t and t squared, where should these go? Under this coordinate vector here. So let's write down this. So what's the coordinate vector for 1? Okay, and then what's the coordinate vector for t? And similarly, t squared. Okay, so to answer this question, right, you should ask yourself, how you gonna send a general polynomial to R3? Let's say I give you a plus bt plus ct squared. What's the coordinate basis here? Sorry, coordinate vector here. A, B, C. So what's the coordinate vector for 1? What's the coordinate vector for 1? 1, 0, 0, because A is 1, right? B is 0, C is 0. T, 0, 1, 0. And then T squared, 0, 0, 1. Because A is 0, B is 0, C is 1. But what can you see here? Why is 1, 0, 0, 0, 1, 0, and 0, 0, 1 in R3? These are the standard basis. So you know that these standard basis form a basis. They are linearly independent and span. So you can use the fact that the coordinate vectors span R3 and linearly independent to imply that these three polynomial here also span P2 and linearly independent. Okay. If you don't believe me, you can go back and go through, use this coordinate vector here, apply it to our calculation here. And then the calculation we did here is exactly the finding pivot problem here. Yeah, solving the matrix formed by this standard basis. Okay. Yeah. So let me do a conclusion here. the fact that the image of 1, 2, 1t and t squared under the coordinate vector mapping is what? Is linearly or are the images are linearly independent and R3 implies that 1t squared also let's quickly write the both thing, also form a basis for P, P2. So note that here there's a clever choice here. Because you choose 1t and t squared here, only that they correspond to the standard basis. If let's say you choose a different, okay, if you choose a different basis here, let's say you choose 1 plus t and t squared, then you will send to a different basis in R3 already. For example, 1 plus t, you will get sent to 1, 1, 0. A equals to 1, B equals to 1, and C equals to 0. And this also form the basis, right? Also form the basis of R3. So 1, 0, 0, 1, 1, 0, and 0, 0, 1. Can you quickly see that this form a basis? Because you have pivot in every column and every row. Okay. Okay. Any question? Okay, so in the exam, either you do the traditional way, or if you understand this coordinate basis very well, you can send it to the right Rn first and then check on Rn. Because on Rn, what you need to check? Just find pivot, right? But in vector space, depend on your operation inside your vector space. Okay, understand? Okay, but before applying coordinate vector, make sure you know how to find a nice basis for your vector space first. Okay, this is the key. Okay, if you pick a different vector, if you pick a different basis, then it corresponds to a different set of bases in your Rn. So in this case means what? Here is the place to go to every vector space. But on the left-hand side here, okay, is just Rn. So meaning what? We reduce everything from finite dimensional vector space to Rn. Note that here is finite dimensional because our basis is a finite number only. So the key here is what's the upshot here? The upshot here is the coordinate vector mapping reduces the question on finite dimensional vector space to Rn. Okay, so let's say n dimensional vector space. Okay. And in Rn, we solve by matrix method. So that's why we study vector spaces, because in vector spaces, we can reduce our problem into Rn if the vector space is n-dimensional. N-dimensional is quite big, you know. I mean, in real life, maybe you have a lot of variables, not just one, not just two, not just three. For example, stock market, right? Stock market, what you need to consider? There's a lot of index, you know. Anyone play stock here? No money to play. So if you look at the stock market, there has a lot of index. Okay, they have to consider what's their liabilities, what's their costs, right? What's their earning, what's their profit. So there are a lot of criteria to check. Okay, so you can regard all these criteria as your variables. Right? Maybe it's a R50 or R100. But no matter how big R1 million, you still can solve it using matrix method. And then this is what your computer can handle. Okay, this is what your computer can handle. Okay, maybe you cannot handle, I also cannot handle, but your computer can. Okay, as long as it is finite. Okay, any question so far? Any question? Any question? No? Okay. Maybe we go a bit longer so that we take break before quiz. We have 2 break, but second break make it before quiz. So let's go a bit longer, then we will take a break. Okay. Right. So let's go a new part here. So change of basis. Okay. So before change of basis, let's motivate it a bit. So let's motivate. Okay. So the motivation is very simple. Again, R2 to take R2 here. So last time I showed you 2 different bases, right? 2 different bases. So let's say first of them we take the standard basis 100. And then second, we take a different basis, let's say 1011. So you can easily see that they are the basis for R2, because if you look at the matrix formed by the matrix with columns formed by this vector, you will check that there are pivots at every row and every column. Okay. It's nice to check because I purposely made 0 below one of the pivots. For this one, I simply put 2 also can, put 3 also can. All of them are different bases. Okay. Right. So what is the accent of this change of basis here? So let's say we have this an element in R2. Let's say how about we look at, okay, let's draw some picture here. So linear algebra is nice with picture. So let's say this is 1 2 1 1 1 0, and then 0 1 here. And then if I change basis, right, I kind of tilted the y-axis to 1 1. So let's pick some non-trivial vector here. Let's see, how about pick 2 1. Let's pick 2 1. Okay, so where's 2 1? I think 2 1 supposedly to be here. So what can you see here? What I do is I pick this vector such that it lives on the first quadrant on the first basis. But if you look at the different bases, it lives in the second quadrant, left to this the other basis vector. So let's check the coordinate basis, both coordinate bases here. So let's check I call it the address, right? So let's check the address in different bases. Okay, so this is equal to what? Still 2 1. Okay, why? Because how do we get this coordinate basis? This is the coefficient when you try to express as a linear combination of the basis vector. Okay, so this is how I get this 2 and 1 from. How about in the other case? Is it possible to do it by inspection? So maybe you need the reason first. What's the reason here? So what's the thing you need to multiply before 1 1? Okay. Oh, sorry, I picked the wrong guy. I don't want 2, 1 here. What should I want? I should want 1, 2 here. Okay, so that it go higher. So let's change this one. Okay, morning. Okay, so if I want to find the coordinate vector for 1, 2, what happened? What's the 2 coefficient I need to put here? -1 and 2, good. Okay, so you can do this by inspection, because you need to see that here is the second term from the first vector is 0. There's no way for you to build this 2. Okay, you must build this 2 using the second vector. And then you try to adjust the first term from the first vector. So you get this. Okay. So what's the analog you can see here? 1, 2 doesn't change in the chart or in the graph. But what's changed is the coordinate vector. So how should you imagine here? Maybe you live in this land now. Okay, let's say this land is not Malaysia anymore. Maybe China took it away. Then your address have to change. Okay, so if you change this basis, right? Okay, then your description on your vector will change. So you can see that it makes sense, right? Why this vector gets sent to -1, 2. Okay, because you are on the second quadrant, so you are negative. I mean, you are taking one of the negative of 1, 0 and then 2 copy of 1, 1 to make this 1, 2. Okay, so you are taking this 1 copy of this and then 2 copy of this. Okay, so that you can make this vector. Okay, another way to think about this basis is like a ruler. It's like a ruler. Okay, it's like, okay, how many pieces of these vector you need to build your vector? Okay, okay. So now the problem is, can we go between these two or not? Is there a way to go between these two? So meaning, is there a way to go from 1, 2 to -1, 2, given that we know these two things? Do you think so? Is there a way or not? To go from 1, 2, right? Is there a way? So the question is there a way to jump from 1, 2 to -1, 2, given that we know these two bases? Okay. So think about it. If you want to input a vector with 2 entry and then produce a vector with 2 entry, what's the if this is a matrix transformation, let's say if it is a matrix transformation, what size of matrix you need? In this course, map between vector spaces usually is linear transformation. If it's linear transformation between finite dimensional space, you can use a matrix. Okay, so what size of matrix you can put here? Such that you input an R2 vector, output an R2 vector. What size? What's the size? You understand what I'm asking or not? Okay, what's the size? What's the size of what m, what n? Okay, multiply 2 times 1 equals 2 times 1. 2 times 2. Okay, so you need a 2 times 2 matrix here. Okay, is it possible or not to cook out a 2 times 2 matrix here? Okay, so this is the motivation. So let's try this example. Okay, let's try this example. So consider the basis B1, B2, and C1, C2. I didn't even tell you what is B1, B2, and C1, C2. Doesn't important, not important. Okay. Let's say what we know is how we express B1 in terms of C1, C2, and how we express B2 in terms of C1, C2. Why can we do this? Because C1, C2 is also a basis. And B1 is a vector inside your vector space. Okay, so it should be a linear combination of C1 and C2. So I want to say that this is true because B1, B2 are elements in the vector space. Okay, so let's add something into this question here. Basis of vector space V. And C is a basis. So we can do this. Okay, we can write B1, B2 as a linear combination of C1, C2. So the problem is if X is a vector in R2 such that the coordinate vector in B is 3, 1, you want to express it in a different basis. You change basis. See how the coefficient change. Okay, so what do you do? Okay, in this class, you just apply the definition first. Okay, so apply definition. So what does this coordinate vector tells you? X equals to what? 3 times B1 plus 1 times B2. But now you want to do what? Find the scalar. If you're gonna express in terms of C1 and C2, can you go from B to C or not? Can, right? Because this two equation tells you what is B in C1, C2. Okay, so we just substitute. Okay, we just substitute. One times so this one becomes 6. Okay. Yeah, but you can see that there are two C1 and two C2 here, so we're gonna combine them. So if you combine them, what happened? Anyone got it? Anyone got it? 6 C1 plus 4 C2. So in other words, the coordinate basis of X in C is 6 and 4. And 6 and 4. But surprisingly, so just now I asked you a question, right? Let's say how to go from this case, how to go from 3, 1 to 6, 1, 6, 4 by a 2 by 2 matrix, right? Can you reckon what's the 2 by 2 matrix you need to put here? From this, guess from this calculation. You guess from this calculation what matrix you need to put here. Right? 36, 1, 1. So you check first. First you check is it correct or not. So if you do this multiplication matrix vector multiplication, you get 6. 4 times 12 minus 6. 6. 1 times 3, 1 times 1, 4. But this calculation is what you have written before, right? 4 times 3 plus 1 times negative 6. And then 3 times 1 plus 1 times 1. Okay, but another thing is, where this thing come from? Where does this thing come from? You need to be sensitive to number. Where does this thing come from? There's another place this thing come from. Can you reckon? 4, 1 minus 6, 1. This is a coefficient of someone else. Whose coefficient? It's actually the coordinate vector of B1 and B2 in C. Okay, so meaning what? Meaning, once we know how the basis of B looks like in C, we can send every vector coordinate vector in B to coordinate vector in C. Okay, later we're gonna prove. Okay, maybe if not proof, was look at this theorem later. Okay. Yeah. So this is the matrix you want. Okay. To know how to go from coordinate vector B to coordinate vector in C, you need to know how the basis in B looks like in C. Okay, so later we'll see a general form. And let's break until 10:10.
就是格式，它是就是等一下，这个处理，然后它会写成这个样子，这个。
哦，对不起，我要调。我们不要这样写。我在哪里又这样写？
这个是
哪一个？
讲就是6，
有做一个调整，
就这个。
给我看一下哪里写。Right， 这个哦，哎，你这个是我黑板上的东西，对，我有更新那个 lecture note，你有下载吗？你要去下那个完整版的，不是 Blackboard 的。
这个就是
长江的。
一开始。
对，我好像更新了呀，放一个 transpose 在上面，把它变正。
所以就是这样写，就是第一种那样，应该是。
对，就是我上课其实一开始讲那个形式呀，因为有时候我会混，因为我在分享。对，这个算错了。
是不是？
嗯哼，
这个是 column A 是 R 级，它是
对喂，等一下，是一个 subspace in R， two dimensional subspace in R。
然后什么呀？为什么这个也是跟那个一样？这个靠是R5是4，然后除13。
你说哪个 ？Now A，P 是3，Q 是4，对，没有错。
为什么？
因为 Now A 是 A 乘上的东西等于0。A 可以乘水 ，A 只能够乘3乘1的东西。对，然后 column space 是这个 column vector span 出来的一个 subspace，所以它这里的 vector 全部是活在 R4里面，所以 R4的 linear combination 肯定还是 R4。
有没有 row？
也可以，所以 row space 其实跟 now A 是活在同一个 R 上一个 vector space 里面，但是它们应该是不同的 subspace。因为你算 now A 的时候，它有一个条件嘛，它只能够是让它等于0的一个 subspace， 但是 row A 的话是拿它们的 linear 直接拿。
就是 subspace 是向量，就是数字，然后这个 R 级的级是一样的。
对，没有错。
级是一样，但是数字是不一样的。
不应该讲数字不一样，因为 subspace 本身数字就不一样，就是你就说 subspace 不一样了，就是说它 span 出来的
嗯，
空间不一样。
那 subspace 是一个什么向量吗？
subspace 是很多个项，subspace 里面有
个向量，
好像2个，
就是像这个，然后和这个。
哦，你是说
这
不一这个只是说它的 dimension 是2，但是它可以是很大很多个 dimension。
嗯
span 啊，你的概念应该要抓的是 span，就是说 span by 几个 vector。
这个是
这个是你说这个是不是这个 subspace 啊？这个不是个 subspace，你知道为什么吗？subspace 的定义有3个条件嘛？
是零在
对，零在里面，对。
然后第二个是
加起来
C 加 V
对
在里面。
对，你看啊 ，C 加 V 啊，像你画这个东西就不在里面了，它就出去了。所以它不是个。
这整个它是一个，就是4块，它
是一个，因为这个就是 R2 本身。Okay, you want to see the notes, is it? You want to see the quiz? Okay. Yes. Others, right, that want to see. Maybe you can take the photo. Benny? Okay, you can take a photo of it.
Okay.
If you don't understand, you can. Hello. Is Hiba here? Hiba? Okay. Nguyen, trying to see your quiz. Can take a photo. So you can check answer with my solution on photos. And then if you have any problem, think you have more marks, you can ask for me.
Yeah, sure.
When you take a photo of the quiz, because I need the hard copy.
Can have like 4 absences with them, so because I was late coming and if you could like not mark me absent.
I think you can let your AA
I'm sorry.
because you say you join the class late, right?
Yeah.
So you can let your AA know so that he or she can not be fired.
Okay.
Yeah, because he or she is supposed to know. That's right. That's right.
From Tunisia, like late.
Okay. Yeah, you just let your AA know. That's fine.
Okay.
Yeah.
Thank you.
Okay. Yeah. Okay, so you can see the quiz solution online. Yeah, and then you can see which part you don't understand or which part you think maybe I missed much. Then you can tell me.
Hello. Okay. So let's start. Okay. So notation. I want to remind you about notation about row A. Okay, row A. Although we cut our matrix in a row vector form, but we still write our row vector form as a column vector. So in this case, if you see the updated note, I put a transpose on that row. So if you transpose this 1 times 5 matrix becomes what? 5 times 1. Okay, actually a 5 times 1. So be careful. Although we mentioned row vector, we still write it as a column vector. Because I don't want you to confuse. I don't want you to confuse with vector in Rn with matrix. Not a big deal, but I don't want you to confuse. Continue. Okay, so the definition or theorem is this. So if you have a general basis B1 out to Bn, and the second basis, you should expect that C here should also just end with Cn. Why? Do you still remember last time? There's a theorem says what? If the number of the bases is n, you change the basis, your number of bases won't, because dimension vector space attached with one dimension. Okay, won't change. Okay, not change the n. So then there exists a unique matrix. Okay, call it P from B going to C. Okay, maybe you would think that it's weird here. Weird here. If just B going to C, why not write like this? What do you reckon? Isn't it? Okay, but later we will justify why we write in a backward way. Okay, so PB to C such that the coordinate vector in C is equal to this matrix. Actually, we call this change of basis matrix. So I think let's name it change of basis. Change of basis matrix. Okay, from B to C times the coordinate vector of B. And how do you form this matrix here? Exactly, you take all the B1, the coordinate vector of all the B1 in C. And you can see that it is invertible. Okay, why is it invertible? Why is it invertible here? So maybe quickly do this. So why is it invertible? What do you think? Why is it invertible here? So this PC, PB to C, right? What size is this? What do you reckon? What's the size of this matrix here? What's the size? What's the size of this matrix? How many number of columns? N. Okay. How many number of rows? So number of row concern what? Concern with what? The number of coefficient you can put in. So how many number of coefficient you need to put in to express in terms of vectors in C? How many vectors in C? N. Okay, so this matrix is a square matrix. Okay, it's the n by n matrix. Okay. So if you want to say that n by n matrix is invertible, right? What are the equivalent segments? You can check that. either every column and or either every column are linearly independent. So what? So what? Okay, so let's give some more info here. So this coordinate vector, right, is a map from where to where? Okay, maybe going from V to Rn. Okay, so you want to speak about whether these Rn vectors are linearly independent. What? Like what we discussed at the start of the class, right? Because this map is a isomorphism. If you want to ask these people are linearly independent or not, you can ask whether these Bi are linearly independent. But these Bi are basis. So basis is automatically linearly independent. Okay. So we will have that the column of this P to C is linearly independent. It's linearly independent. Okay, because Bi are linearly independent. Okay. And then since P, the change of basis matrix from B to C is a square matrix, then P of B to C is invertible. Okay, invertible means what? Invertible means that so the inverse of this matrix exists. So now we want to find who is this basis, who is this matrix here. Okay, who is this matrix here? Well, let's start from the coordinate basis of B. Okay, this is equals to the, let's say, identity matrix times this coordinate vector. So let's consider this, and this is equal to what? P of B to C inverse times B to C. Yes. But what do we know? We can combine these two together. Okay? Combine the last two. If you have a change of basis matrix and a coordinate vector in B, what happens? You send it to coordinate vector in C. B becomes C. Very straightforward notation, right? Then B becomes C. So this calculation become P B to C inverse of. But what does this mean? The matrix that multiply to a coordinate vector in C become coordinate vector in B. This is actually what? This is actually the guy from coordinate of C to coordinate of B. Right? This is by definition. So these two together is actually the same. Okay. Okay. Any question? Well, maybe some of you a bit puzzled, right? To show you a full calculation here, maybe very quick. Also, not that. Okay. Let me show you a very rigorous way to see it. This is also true. Okay, so we can, let's say this is number 1, this is number 2, right? We can take 1 minus 2. Or if you don't want to use the minus 1, you also can substitute. So this is true. Okay, but what can you do with this matrix vector multiplication? You can group them together. Okay, but you should imagine yourself, what kind of matrix, okay, that multiply to any vector you get 0. So this implies that this difference here must be a 0 matrix. Okay, they must be equal to 0 matrix. Okay, so they are equal. No. Okay, because this has to be true. This equation has to be true for x. Yeah, it will be true for x. So the only way is to multiply 0 matrix. And so they have to be. Okay. Yeah. Okay, so this is the part to explain the inverse. Yeah, the inverse of a change of basis matrix is just swap the arrow. Right? Just swap the arrow. Okay, very intuitive, right? Right. If you want to go back, to be just swapping arrows. Yes, it is true. Like just swapping arrows. Okay, so let's continue. So let's see this theorem in this example here. So how to find actually in general? Okay, let's see in general how to find. I will guide you do A first, and then I'll let you do B. Okay, I'll guide you do A first, and then let you do B. I think we will follow the construction in your textbook. Your textbook is quite good. Okay, let's follow your construction in your textbook. Okay, let's do A first, and then I'll let you to try B. Yeah. So now we're gonna find change of basis matrix from P to C. Okay, so meaning your P is going from beta to C. So what do you do here? Okay, so the first thing you do is you need to ask yourself how your B sit inside your C. You need to ask yourself how your B sit inside your C. So let's so we need to find these x1, y1, and sorry, x1, x2, and y1, y2. Okay, then what does this mean here? By definition, okay, why we want to find this? Because just now the theorem tells us that this change of basis is exactly formed by this B1 C and B2 in C, the coordinate vector of B1. So we need to find them. Okay. So how do we find them? We will use a very economic way to find them. Instead of substitute. You can do that if you like. Otherwise, we will use this the augmented matrix that you learned before. So by definition, what? Okay. You take the linear combination between x1, x2, sorry, linear combination using C1, C2 using this scalar, you will get B1. Okay, so how do we write this? So this is a more advanced way to write a linear combination. So C1, C2 times x1, x2. Right. So let's see. Let's verify this. Hey, hello. So let's verify this. So here is a 1 by 2 matrix, right? And then 2 by 1. Okay, so if you multiply them together, you should get x1 times C1 plus x2 times C2. Okay, so this is a fancier way to write linear combination. Okay. So this is a fancier way to write this linear combination. But this fancier way is useful later. So similarly, we have C1 times C2 on Y1, Y2, we should get B2 here. So we try to solve this together. Okay, so how to solve this together? So to solve this, them together, it is equivalent of C1, C2 augmented by B1 and B2. Okay. We put here. Here is two set. Oh, not use set. Two linear system. Okay, two linear system here. Okay, and then let's write it down. So where's C1, C2 here? 1, 3, minus 4, minus 5. And then minus 9, minus 5, minus 1. Sorry, 1, minus 1. Okay, so if you try and do this row reduction here, so let's skip the step 1, 0, 0, 1, you will get 6, 4, minus 1. Okay, so in this case, what does it say here? So this implies that your solution B1 in terms of C is equals to 6 minus 5. And then B2 in terms of C is 4 minus 2. Okay, so your P is written as what? Hence, your P from B to C is equals to 6 minus 5, 4 minus 3. Okay, so how to justify this notation here? Because if you find your matrix in this way, so this part here will become your P, B to C. Why is it written in this way? Because when you solve this augmented matrix, you indeed put your basis in B on the right hand side, and then put your basis in B on the in C in the left hand side. Okay, and then after you row reduce the C part to identity, what's left over is a change of matrix from B to C. Okay, so you can see that the B to C is like this. Okay, any question? Okay, any question so far? Any question? No? Okay, if no question, I give you 3 minutes to work out part B from C to B. Okay, let's use the exact same way to compute C to B. See if you get the right answer. Maybe I do together with you because I also don't have answer. Let's compute C to B. Yeah? Testing. Okay. Did everyone get this matrix here? Negative 3 over 2, negative 2 over 2, 3. Okay, you got it? Okay. So also that you can check your answer actually based on PBC. Based on PBC, you should be able to check your PCB because just now we know that they are inverse of each other. So you can multiply together such that you get identity. Right? This is one way of checking. Okay. Anyone not get it? Okay. So what do you do? This notation here suggests a very good algorithm for you. You should put your C on the left hand side and then put your B on the right hand side and row reduce it until the B basis become identity because you can, right? Because B is a basis. So the matrix is row equivalent to identity. So you must be able to do it. And then what's left over is your change of matrix. Change of basis matrix. Okay. Make sense? Okay. Okay, so the theorem is this. Okay, so the theorem is if you put this is not restricted to two bases. You can put like C1 up to Cn. Okay, you can put C1 up to Cn here. So in general, you should have C1, C2 up to Cn with B1, B2 up to Bn. Okay, is row equivalent to identity with your P going from beta B to E. Okay. So this notation here suggests you how to arrange your matrix. And put B on the left hand side and then put C on the right side. And then the inverse, okay, the inverse of B to C is just C to B. You reverse the arrow. Does it make sense? Huh? Okay. Any questions so far? Any questions so far? Any questions so far before we leave chapter 4? We're gonna enter chapter 5. Yeah, no question. Okay. So let's enter chapter 5. Maybe in the start of the next lecture, we will revise a bit on chapter 3 and 4. So this week is on quiz 2 is on chapter 2, right? So next week will be on chapter 3 and 4. Okay. All right. Right. So let's see. Okay. So let's motivate the next chapter. So the next chapter is about a very new concept to you. Maybe you in your life you never think about it before. So this is called eigen values and eigenvector. Anyone heard about this word before? Eigenvalues and eigenvector. Heard about it? Where did you hear about it? Oh, QM1, QM1. Oh, you only have QM. Okay, good. Okay, right. So do you know what's the idea behind this? No, huh? Okay, so I'll let you see the idea. Okay, so basically, we are concerning about this equation here. Okay, I mean, linear algebra is just equation, right? Bunch of equation. Whether that answer is 0 or something else. Okay, so this, in particular, this equation here is concerning about AV equals to lambda V. So lambda is a scalar here. Okay, and then A is a matrix. Let's say let A be a M times N matrix. Let's say my matrix is M times N. What should my V be? Where should my V live? That's you. So where should V live? Rm or Rn? You must be very certain in this answer already. Rm or Rn? are n. Okay, so they can multiply together, right? M times n, n times 1. Okay. So what's this about? So like I mentioned to you, right? LV live in where? Span of V. Span of V, right? Yes, scalar multiple of V. Meaning what? You take a vector V, you send to where? A scalar multiple of V. Okay? Either you make it long or either you make it short. Okay, so this is the content about eigenvalue and eigenvalue. Okay. So we will call what? We'll call lambda as a eigenvalue and then V as a eigenvector. Okay, so meaning if you input an eigenvector into your A, it will output a scalar multiple of your vector. For example, what kind of matrix transformation would it be? For example, this particular matrix transformation here. Okay. So how do I devise this transformation? Actually, this is 2 times the identity matrix. Okay. So this is a map from where to where? I'll test you again. What can you multiply to A, and then what can you get from it? You output what R and R2 again. Okay, so this is a map between R2 and R2. Okay, send point in plane to R2 the plane again. So what does this map do? So let's take a general elements here, xy. Okay, and then we multiply 2, 0, 0, 2 to xy. What do you get? You just get 2x and 2y, which is 2 times xy. Okay, so in other words, what happens? What happens? What happened to your point in R2 here? Okay, if you consider all the points, right? All the vector become longer. Okay, scale by 2. But except for one vector. You know what's that vector? 0. Good. Okay, so the 0 is remain unchanged. In fact, this 0 vector is not changed by any transformation. No. Anything you multiply to 0, you always get 0. Okay, so 0 is out of our discussion. We won't discuss 0 as our eigenvector because it's always gets sent back to 0. In other words, it's a fixed point. Okay, it's a fixed point for every map. Okay, so should we jump into? Now let's jump into the definition. Okay, so let's define it. So a scalar lambda is called an eigenvalue of A if there is a non-trivial solution. You see, non-trivial solution, we don't take the vector to be 0. It must be non-trivial solution x such that x equals to lambda x. Okay? And then such x happen is what we call an eigenvector that correspond to this lambda. Okay, so eigenvector will be attached to this lambda here. So they are together. Okay, one lambda maybe have more solution, like what we calculate before, right? A linear equation could have more solution here. Okay, but let me ask you, if I want to satisfy this equation, right? What do you need to solve for actually? How do you solve it? If what I want to like satisfy this equation here, how should I solve it? Okay, first of all, A is a matrix, but on this side is a vector. And we combine these two things together. For example, so one thing I want you to think about is, can we like write this? I mean, we can certainly write this because this side is R, let's say, okay, let's make this A to be M times N matrix. Okay, so both sides is Rm. Okay, so we can do this. But this is a vector equation, right? So supposingly we can build an augmented matrix. But what's the coefficient matrix here? Say something. Oh, Hiba, you try? You want to try? R minus, you mean like this? A minus lambda? What do you say? What do you say? Sorry? A number. Different, sorry. So to find the solution, meaning you need to find the null space of A minus lambda. Okay, so this is what you can think about here from this definition here. All right, so let's try some example. So the example says that whether U and V are eigenvector of A or not. Meaning what? So the question we want to ask you whether A times U equal to some lambda U or not, or an A times V equal to some lambda V or not. We can try and compute it. Let's try and compute. Okay, so which one is the eigenvector of A? U or V? U, right? Okay, do you get the lambda to be -4? Yeah, okay. So if V is not a eigenvector, how do you prove? How do you prove that it is not some scalar multiple of V? How do you prove it? You cannot say, oh, I cannot see a scalar multiply to it, so I cannot. You cannot prove like that, right? So how you gonna say you cannot write it as a scalar multiple? But before that, is this correct? No? You get this? Okay, so why Why cannot I write it as a scalar multiple of 3 minus 2? What question is this asking? Whether these two vectors are linearly independent or not. Okay, so meaning what? If you try and row reduce 3 minus 2 and nine, 11, you should get. So to see, so I just write it down. You can go back and show yourself to see that minus 9, 11 is not scalar multiple. Minus 2, so that they are linearly independent. Okay, they are linearly independent. Okay, you cannot say that, oh, because I cannot find, so don't have. Cannot find doesn't mean don't have. Be careful. Okay. So if you want to prove something doesn't exist, you should show that. You can use contradiction. Suppose it exists, and then there's some contradiction. And you cannot say that I cannot do it, so it cannot be done. This is a very wrong concept. And in our society, you notice in your workspace, in your study space, even with your lecturer also like that. Yeah, some lecturer also think like that because it's normal because they are also human. It's not that you cannot do, it cannot be done. Maybe someone else can do it. Okay. So if you want to prove that one thing cannot be done, you need to show that it is impossible to be done. Okay. Or you can use contradiction. Okay. Suppose it can be done. Then something will contradict something that is true. Yeah. Okay. Okay. How about next part? Show that 7 is an eigenvalue of A, and then find the corresponding eigenvector. Should I make a conclusion here? I haven't made conclusion here. So let's make a conclusion here before we left. So U is a eigenvector of A, but V isn't. So, okay, so now you want to ask a question whether there exists. So for the second part, let's use a different color to differentiate. Whether there exists a V non-zero such that AV equals to 7V. So you want to ask this question, whether there exists a non-zero solution. To solve this, like what I discussed with you just now, right? This is equivalent to n minus 7I times V equals to 0. But you note that A is already given. So it's 1652 minus 7 times the identity matrix. Okay. And then if you combine A minus 7I is just one matrix, right? What is this matrix? Matrix. Minus 6, 6, 5, and then minus 5. So minus 5. Yeah, good. So this is solving this the matrix here. Are you happy if you see this kind of matrix? Are you happy? Why, Edward? Why are you happy? Edward, why are you happy? Sorry? 5/6. So you can see that if you scale one of the, they have one, they have the same ratio, right, for both of them. Okay, so So what you do here? Well, I mean, you just scale both lines first, make them into one. You can even make your pivot first. So you scale both line, both row. Okay. And then what did you see here? Can you dictate that there's only one pivot here? Can you dictate there's only one pivot here? So if you're gonna do next row reduction, what happened? 1 minus 1, 0, 0, 0, 0. Yeah, because you can take row 2 minus row. So there's one pivot here. One pivot here means what? S2 is free. Or in this case here, we call it V2, V1, V2. So V1 equals to V2, and then V2 is free. So what's the solution here? Yeah. So the parametric vector form becomes important here because we want the vector. And so what's the vector here? V2 times 1, 0. 1, 0, 1, 1. Okay, so this means what? Actually, there are infinitely many solutions. This to this AV equals to 7B. Want to check? Should we check? Let's check. Let's do some sanity check here. Okay, let's do sanity check. So let's say we take V2 to be 1, 1, okay? Let's do it on 1, 1. Okay, so what should you expect? Before you calculate, you should expect something already. Because we say that this should be the eigenvector with eigenvalue 7. So you should expect that you get what? 7, 7. Right, 7 times 1, 1. So do you get 7, 7? 1 plus 6, 5 plus 2, you get 7, 7. Okay? And then imagine if you multiply any scalar to this guy here, any scalar, let's say S2 lah, call it S2. Okay? What you should know from the matrix multiplication is I can straight away bring the x2 out first. Okay? Still, I get what? 7 times x2 times 1, 1. Okay? So indeed, there are infinitely many solutions. Okay. Any question? No? Clear? So if I want to make a conclusion is all multiple or all scalar multiple. Okay, not just scalar multiple or non-zero scalar multiple because we don't want the zero vector. Or non-zero scalar multiple of 1, 1 are eigen vector of this matrix here of A. Okay. What time? So let's see. Okay, we have 20 more minutes before we take break later before quiz. Let's continue. Okay, let's continue. All right, so what we can make a conclusion here is the set of all solution of A minus lambda I times X is equal to 0. It's just the null space of the matrix A minus lambda I. So the question of asking whether finding solution to AX equals to lambda X become a question about finding the so we need null space. Have we learned null space yet? We learned null space, right? Yeah, we learned null space. Okay. Finding the null space now. So we learn now, right? Now A minus lambda. Okay. So meaning what? In the previous chapter, you just find now of some matrix. Okay, but now it's a specific matrix, A minus lambda. Okay, it's a specific one. A specific A minus lambda. And then obviously this set is a subspace. Why? Because we have proven that now A is a subspace for any A. In particular, this A minus lambda I is just another matrix. Okay? And then we call this space our eigenspace also. Okay, but this eigenspace is not eigenspace for A minus lambda I. It's a eigenspace for A. Okay, such that AX equals lambda X. No? So in other words, if I want to write is maybe eigen of A equals to the null of A minus lambda I. Okay, so this is the, how to say, the subtlety. So it's a small difference you need to notice here. When we talk about eigenspace of A, actually we are talking about null space of A minus lambda I. Okay, so the subject change. One of them we look at A, the other one we look at A minus lambda. Okay, so please don't confuse, because a lot of students confuse actually. Okay, but please don't confuse. Okay, so let's do one more question here. Do you want to try? I'll let you try this question without telling you how to do. Let's see if you can put things together. I give you 3 minutes. You can discuss with your friend. I'll let you try. All the words here I already tell you what the meaning already. See if you can put things together or not. Okay, so let's decode what this question is asking. So let A be a 3 by 3 matrix. So we have a square matrix here. So we can try and find whether there's an eigenvalue or eigenvector. And one information it gave to you is an eigenvalue of A is 2. Meaning what? Meaning 2 minus, so there exists non-zero vector such that AV equals to 2 times V, which is equivalent to what? A minus 2I has non-zero solution. Okay. So now the question is find the basis. Okay, find the basis to this basis. So you might ask a question, hey, why? As long as there is a solution to this homogeneous linear system, it will form a basis. You ask this question. Will form a subspace. Why? Okay, first thing is now space of a matrix. Okay. Yeah, the second thing is if there's a non-zero solution to this V, right? Any linear combination will be living inside it because we already showed that now A is a subspace. Okay. Linear combination. Close under addition, close under scalar multiplication. Okay, so once you have a non-zero solution there, first all the scalar must live inside there. Okay, so as long as you have one non-trivial solution, the whole line is inside there already. If you have more than one, if you have two, maybe the whole plane is inside there. Okay, so then you are asked to find a basis. Okay, so you are asked to find a basis. Once ask yourself, the minimum write it as a span. 2I is what? Anyone computed? Okay, Edward, ask Edward. Have you compute n minus 2I? What is it? And all the same. So are you happy? Happy again? Okay, why? Because very easily to do row reduction. And you can use row 2 minus row 1, row 3 minus row 1. So easily you get this to 2 minus 1, 6, 0, 0, 0, 0, 0, 0, right? Okay, and then you find your pivot. Okay, pivot. Okay, so what did you see here? You see that there are only one pivot, and your V2 and V3 are free. V2 and V3 are free. So meaning what? In this form here, so your V, so your parametric in parametric vector form. So that's why we train you writing your answer in parametric vector form, because we want vector solution. Okay, so what's this? V2 times half 1, 0, and then plus V3 plus so minus 3, 0, 1. So this is the multiplication. Okay, so this go back to what Senai asked us, right, in the beginning. Okay, so you found that the solution is span of these two vectors. So what's the basis here? In fact, both of them are the basis vector. Okay, so let's write that this is in the span of half 1, 0, 2, 1. But in fact, this guy a bit. In fact, the two vector will form the basis for your null space. These two vector form a basis for now a minus what's the 2I, which is the eigenspace of A. Okay, very good. Yeah. picture to show you or not? Okay, so what happens? Let's see. Everyone okay or not? This part? Okay. Okay, so let's see what happened in the geometry. Let's see. Okay, maybe not show you this. I also have it. Okay, so let's see what happened to this geometry. So, well, this is a map from where to where. So this is a map from, you can think of the matrix as a matrix transformation from R3 to R3 here. Okay, so you have two R3 here, two pieces of R3 here. Okay, the matrix transformation is just multiplication by A. So if you look for these two vector here, okay, this two vector here, it will span a plane. Okay, because two vector will span a plane. So let's say this is the plane. So what happened to this plane is the non-zero vector here get scaled by 2, become longer. Okay, every non-zero vector on the plane will get scaled and become I cannot say become bigger, it's just the same plane. Just that a particular vector gets sent to a longer vector. Can you see it gets longer for all of these? Can you see or not? Yeah, zoom in a bit. Can see? 4 of these vector get scaled. Okay. See? Before touching the boundary here, this one touch the boundary. Okay. Every non-zero vector on this. Vector here. Notice very small subtlety here. You see, there's like how to say this? You see a black axis, right? But you also see less black axis here. So this plane actually tilted. If you try and plot up your 120, where is 120? 120. So you go 1 on this direction, x1 direction, and then go 2 in the next x2 direction. So your 120 is around here. So why your plane is slanted? Because of the other one. Where's -3? -3 in the, sorry, in this direction. -3 in this, sorry, -3 in this, -3 in this x1 direction. And then x2 direction is 0. And then you go out a bit here. Okay, so your plane is slanted out. Slender out on the right hand side. Okay, so that's why you go out on these first and second quadrant here. Okay, you go. Okay, now can imagine? Can imagine, guys? Imagine, ladies and gentlemen. Yeah, you're supposed to see this very straightforward. Okay. Any question? Question? No. Okay. What time is it? Let me count how many minutes. Okay. So let's do one more before we break. Okay, let's do one last piece here. Okay, so a theorem is, so a theorem here. Okay, a theorem. The eigenvalues of a triangular matrix are the entries on its main diagonal. Okay, so how do we show this? Let me give you an example first so that you can imagine this. So if A equals to, let's say, 3, 6 minus 8, 0, 0, 6, 0, 0, 2, and then this is a triangular matrix. So the eigenvalues, so eigenvalues of A are few. So what do you think? 3, 0, and 2. Very good. Okay. So how do we see this actually? How do we see this? How do we see this here? Okay, so let's quickly let you see. So let's do a proof sketch. Let's do it on a 3 by 3. So you can imagine on an n by n matrix. Yes. Let's see from a 3 by 3 matrix. Let's see. So upper triangular, let's do upper triangular. Lower triangular is the same. Upper triangular, lower triangular means where are all the zero. So let's say all the zero lies in below first. Okay, so the claim is these main diagonal terms are the eigenvalue. Okay, so what do we do? Let's look at this minus lambda I. Okay, if we take this minus lambda I, right? So what happened? Okay, so what happened here? We will get A11 minus lambda, A12, A13, A22 minus lambda, 0. Great, this one A. We want to make lambda minus 0, lambda minus A22 equals 0, and lambda minus A33 equals 0. But how to do that? How to do that? That, what, what we want to solve, and only if what? A minus lambda I x equals 0 has a non-trivial solution. Okay, has a non-trivial solution. But it has a non-trivial solution means what? If when you solve the REF, what does it mean? What does it mean? How to have trivial solution? Can you have all of them pivot column? Cannot, right? You must have at least one free variable. Or if only if the equation at least one free variable has one free variable. But what do you see here? What can you see here? These are all the leading entry. So meaning what? If only if lambda minus 1, 1 equals 0, or lambda minus A22 equals 0, or lambda minus A33 equals to 0. Okay. Any one of them equals 0, you have a non-trivial solution. So these are all the possibilities. Does it make sense? Any one of them equals 0, you have the non-trivial solution already. So these are the eigenvalue. Okay, so if you have a diagonal matrix, right, the eigenvalue is easy to read. You just read from the diagonal. This is similar to how we find determinant, right? How to find determinant of the triangular matrix. You also just multiply everything. Okay, so how to say? Triangular matrix is one very interesting object inside the linear algebra. Okay. Therefore, it's yes.
老师，我求出了这个之后，我怎么算它那个什么 Edmond vector？就直接把这两个放到一起吗？
eigenvector 是谁啊？你的问题是谁是它的 eigenvector？
就是对，假如说这个
啊
题它不是说
就是
在这个，
各种的 linear combination 都是它的 eigenvector。
对他们两个的 every linear combination 是它的 eigenvector，
对，
所以就是
这个是，这个也是，然后各种的 linear
都是，
yes。
然后它的 linear combination 或者它自己本身乘上 a 之后应该等于零，
什么等于零？
零向量就是它或者是它的那个 linear combination 乘上 a 之后应该是零向量。
如果你要零的话，你要看 a 减2i。我说的意思是说，你直接拿 a 去乘它，你就会得到二 of
哦，
呀，看你怎么看呢？你要把它看成 null space，就是你要乘的东西是 a 减2i，但是如果你要看成那个 av 等于 lambda v，你只要乘 a 就好了。所以这有两个同样的情况，一个你看这个 a 乘它，或者你 a 减2i 乘它，
看它
呀，都是都是这样的。对对，你可以 try，你可以 try，我建议你去 try，你就拿 a 去乘这个，拿 a 去乘这个，你一定拿到他们的2倍，然后 a 再乘他们的 linear combination，可以直接乘的，因为你要记得的一个条件就是 a 乘一个 scalar 乘一个 vector，那个 scalar 是可以被你拉出来，不知道你记得吗？你如果你回去看那个 matrix operation 的话，就是就是说
肉体乘 vector 那个
不是，就是 matrix 乘 matrix 跟 matrix 之间加一个 scalar 的话，你可以把 scalar 先一路把它拉出来。OK，去 chapter 去 chapter 3。
这是要考的吗？
应该是吧？是这里吧？是这里教 matrix 的人。
是这里叫 matrix。
直接去到它的一开始，应该是在乘法之后，因为我要乘这个。对，你看这个，你看，如果 R 夹在两个 matrix 之间，我就可以直接把它先抽出来，先做 matrix 的 multiplication。
我去试一下。
呀，你去 check 一下。是那个时候。Is 一格 here 吗？无一格here 吗？Is anyone friends to 无一格无一格 missing again. Last way missing, this way also missing. Anyone friends to 无一格？Does anyone know her? Anyone know her? Don't know. Your friend which one SWE202409. There's quite a lot of you here. Yeah, do you guys know her? Huh? 无一格。Actually, you know her? You know her? So what happened to her? You don't know. Whenever reach to quit day, it disappear. A bit dangerous, eh? Like. Okay, so all right. So if everyone ready, right, can you like arrange your row properly, as what we said last time? Let's arrange your row properly. And keep your notes, keep your electronic devices, iPad, handphone, laptop. You can bring your calculator, but I'm not sure it's useful or not. Because we're not testing calculating, so we won't ask you to compute a lot of things. Okay, please keep your phone. All right, if everyone is ready, let's see. Okay, so I think it's the same layout today. Okay, so same rules. Uh, ready or not? Can keep notes, keep notes. We want to start already. Yeah, I'll keep everything. We want to start so that we can finish on time. Well, today only have 3 questions, right? Hopefully we can finish on time. Okay, ready? Please sit back and relax. Keep all your notes. Keep all your phone, iPad, laptop. Okay, if ready, can all of those who sit in the aisles calculate your rows and then come again. You can just start once you get your the paper, but don't rush. You should have enough time. Make sure you write down your name, ID, write it clearly, so that I can see properly. It right. One more. Don't rush. You should have enough time. So we will have 20 minutes. See how it goes. Is Chai B here today? Oh, Chai B, you're here. Okay. Someone replace you somewhere. Edward, have you get your quiz yet? Which one is the wrong? You got click? Okay. Okay, so you have time up to 11:50. Yeah. Since the class have 2 minutes extension, so we'll extend to 52, 11:52. So if you have more time, then I urge you to do sanity check. The class already taught you how to check whether your solution is right or not. For example, if you the equals apply back to identity. So if you have more time, please do sanity check. You can check it on yourself, no need to check with others. I do it on your own, because in final you cannot get help from your friend. Minutes. If done, try and check your answer and see if you write out your name properly. To discuss, because I can see very clear from here. Okay, so please pass your solution to the person in the aisle. Then the person in the aisle, please help me calculate if you have the right number on your rows or not. Open out, please open out your solution and then your name face up. Your name face up. And then pass to the middle. And please make sure your solution sheets get collected. Quick. Try to go back, please, to quick. Yep. Quick. Which row haven't submitted yet? Still writing? Collect from here. Ready? Submitted? Again, make sure you submitted before you leave. Otherwise, like your quiz will go miss. Okay. Time's up. Please make sure your quiz get collected before you leave. Okay. Thank you. Time's up. Hello. Time's up now. Southern and Bryson. 来。Time's up. Make sure your quiz collected before you leave. Hey.
我出东西。不是东西。
出东西。
Elementary 不是做那个东西要顾虑哦。
哪个东西？
我会做那个在做什么？Elementary 就是把这个变成011，然后把这边把这个东西转换过去另外一边。
乱七八糟，给我名字放上面。这样子。Anyone still haven't submitted?
你是在什么名？没有，我点了，因为我是用会是点，如果你会是到的就点了。
其实
不知道吗？答案错了可以提报，但是也不知道。问一下你，就是你
用这个 Elementary 是
要再写那个 B1 Interest B1 B2 这些。
对，做这个东西没有记得的意思。Bridge 那种，
这个只有一个情况，
有没有放啊？
就是 B1 B2 B3的一个情况。
那所以还是不可以这样写啊。
因为前面的题目是解锁任题的。
老师会按这里时间来提醒。我被豆打去。
现在
没有了。
够力啊！
不要紧张，这种所以
这很紧张啊！
不要紧张有用啊！除非你现在抢2跑去嘛，
其实我一开始我懂要做这东西啊，只是我觉得我看到 Elementary 就以为，因为我记得有印象是这东西啊，我做这个。
我看到影子会做到，just do it 做。
哇，如果是这个的话
，just do it 题目要找什么马上做。 不紧张。
你打开来，
没有，因为老师讲，步骤还是有可能，答案错一分罢了。你不要紧张。
那你刚好
因为我没有写解释那种题本的哦，还是找答案写出来的哦，我只给答案的哦。不能是慢慢做，都是慢慢做。我刚刚在打分。
你的，
你不要紧张，你要去监考真的吗？我注意他的偏见。
哎，老师，我问你个问题啊，其实这样都是
等一下
这是 allow 嘛，这也是 elementary road operation 嘛，你是没有答过了。
哦，我多印了几张，原来只有一个人没有来，这样难吗？
089啊，
我印了几张
29个
啊
29个。
我印了
说的 ID
我忘记啊
看来是有好事发生。
什么？
我说的 ID
你谁来？你说
29啦。
29啊？你
其
说
实这样是 OK 的嘛，我记得也是 elementary road
你有
operation，
找到没？你有找到你的什么？
我就是忘记不找了。
可是我跟你进去好像
我懂是这个东西，一开始然后我觉得，因为你看 elementary
对啊
这个
对啊，OK 啊，这个也 OK 啊，这个也 OK 啊，这个也是 elementary，这个是 elementary matrix 吗？这个 OK 啊，
这样是可以吗？
你找到了吗？
那是什么
你
头奖？
找不一样的东西了，你找去什么东西？应该要找去来的，你解完了没？你还没有解完是吧？后面解完了，
他没有东西给他写啊。
还差一步，
还有
差一步，
有个东西在后面，
这个
我还有一条线没有画过，我刚来不及写了。它应该这边应该还有一个 matrix 在这里的，应该是啊
什，么意思？这个
是不是
三个我讲看哦，三个乘在一起啊
全部凑在一起，
就方便纠结。
全部凑在一起就是答案了。
，row one 加 row 3，我再交换，
一开始先交换先，然后就是 row 1跟 row 3哦，一步做嘛，做下来。
在做么？我看看，你这个交换嘛，怎么你没有写出来这个东西等于什么？怎么你只写这个乘这个乘这个？哦，这个是整个1跟2交换哦，对，OK 好，然后
东西应该是对的，只是忘记写的那个最重要的东西哦。
你步骤是对的，看看1跟2交换，这个冷蛇除掉是吧？
OK，不要写步骤没？
不懂，我要看一下，
我的步骤
check 一下，我 check 一下。
我 liquid 掉了，这
啊
样我 liquid 掉我的步骤啊。
而且啊，这个就是步骤来了，其实
今天就要开始改了。
老师有分数吧？这个
应该
你会给我一点分数啊？我真的很伤心耶。
改，
有分数吗？对，有分数了嘛？
应该是有啊，应该是有啊，因为你不到要把它变成 identity 嘛。
啊，
OK，然后再看
你别这样笑。
什么？我不知道，我要看一下。
不然开窍。
刚好
学了这样子。
啊 OK，因为你知道我要什么，
对啊，我们看到题目就是做保，就是都做。
对，没有错，
就是
看这个招吧，对。
如果你讲了太多 proving 的东西，会
嗯
这样好像有点乱去。可是我明白你想要让我们知道我们在做什么，就是 email 的做而已。
对。
那我们做 email 的做。
哎，没有啦，就是说你因为做的时候，你可能会回想。
可是我会懂它的 theory 是什么。
是。
还有之前我不是问你，你只要写 suppose 什么
啊，对，然后
那个我懂了。
你懂了，你讲懂了。
看做久多了啊。
哦，
好，算是什么？你就要讲 suppose
应该不会错完了，应该不会错完，但是我不知道要几分。
是步骤的问题还是什么？是还没看步骤啊？没有看整体啊，整体如果对照完呢？如果东西是算对的，只是
对照完了。
没有把答案搞错啊。
对，我要看一下你做到哪里。
上气啊！
我看到你做到哪里。
我会做这个，只是我觉得，因为我记得 elementary 也是放这个东西。你叫我放这东西，我都以为放这东西。
你知道你少做什么东西吗？我先跟你讲。对，你没有把这一整大串的东西乘在一起。
对，有没有把答案？
对，没有把这时间。然后还有一个东西是你好像没有算完，你还没有听到这一步啊。
听啊，这里啊，
听到没？啊，
我放在就刚好做到这个时候已经到到这里。
这2步在做么？哦，你想要把全部乘在一起。
我没有时间。
没有，你没有时间，你要至少讲你要再做么嘛？对不对？你至少讲 A inverse 等于这串东西 OK， 我没有时间乘。
但是 A 可以写下来，写下来，我给你知道，现在你改成你就忘记 OK。
我抬起来。
Enter table。先当时这样再看。
是对的嘛？觉得就是
对啊，你就是要全部乘在一起了。
啊，算了，
他们是全部乘在一起吗？因为在这一边乘在一起。
这上面哪里可不可以？
可以啊，可以。再看，可以了啦，不要紧张。做tutorial 就可以了。OK。
你
主对热答
有的人还没有做完，你就是在里面不是有讲有的人做第几题没？我们就只做那几题啊，因为刚好去年今天也是这样子做，就跟着他，因为他这课拿10点。
老师谁来的？
应该不是，应该是刘杰学生啊。
去年啊，那这样他跟我不一样，我其实
因为他是刘杰学生。
我是前年的，不一样。
因为你的 Algebra 课很少，不我认识的人，他们讲神经病啊，讲 short 才不会拿 math。
没有，我就喜欢才拿。
Seng 还会拿
啊
，Seng 还会拿数学，
数学
30，拜拜。
那 probability 哦，
我回去啊。
可是没有我的算是 short sem，一个 sem 下个 sem 拿3个 credit，然后我是要拿上一个 art 我嘛。
他要完了嘞。